it myself also, maybe. But I think that's for the sine and cosine. For the sine and cosine, you have a j if you want to write it. I would say here you can use this too. See, you need to calculate cosine hyperbolic gamma, right? And I say, think about it. Gamma is going to be 2 plus j3, right? Now, if you want to calculate the cosine hyperbolic 2 plus j3, it says it's going to be cosine hyperbolic 2, so you can use your calculator to calculate that. Times cosine 3, right? These are radian. Keep in mind, these are radian. Plus j sine hyperbolic 2 plus sine 3. You know what I'm saying? You can use this equation or this equation, either of them. You know what I'm saying? We can use these two equations. You can use these two, or you can use these two to calculate the cosine hyperbolic gamma and sine hyperbolic gamma. When you go through the homework, you see you have to calculate these numbers, and you have to use this equation to calculate. Now, the next is, so we calculated A, B, C, D parameters for the long transmission line, and as you can see, there's a lot of calculation here. We want to make this one a little bit simpler. You know, this is again approximation model. We call it the nominal pi model. Nominal pi model, or equivalent pi model. We call it nominal or equivalent, I think it's equivalent. Equivalent pi model for the long transmission line. If you remember, pi model was for the medium line, right? But we can come up with the same thing, you know, for this one. Let's go remember what was the model for the pi model. If you go back, look at the pi model, we have something like this. For the transmission line, if you remember we had a z, y over 2, y over 2, right? That was the pi model. Here is the VSIS. And here is the VRIR. Right? For the transmission line, medium transmission line, we say left side y over 2, right side y over 2, and middle is going to be z, right? And we went and wrote the equation, and we calculated the ABCD for this system. If you remember, for that system, if I'll go back, let me see what we have. If I'll go back, remember for medium line, we had this thing. We had A equal to, you can double check it to make sure, 1 plus zy over 2. B was equal to, actually A and B, they were equal. B was equal to z, and C was equal to y, 1 plus zy over 4. If you check this one, let me double check it to make sure. Yeah, that would be 1 plus zy over 2 z, right? Yeah. That was what we had for the medium line, right? Now I want to come with the equivalent circuit like this for the long line model. Let's call this one z prime. I'm not going to call it z, but I'm going to call it z prime, right? Y prime over 2 and y prime over 2, right? I put the prime because I don't know what they are. Right now I don't know how to calculate them. I came up with the concept of the pi model I had for the medium line. For medium line, I had this model, z, y over 2, y over 2, right? I'm saying, hey, I want to get something similar for the long line model. So I'm going to call them z prime, y prime, and I'll go calculate them to see how much they are, if I'm going to do it this way. Now, let's come back here. See, basically for this system, based on if we have a model like this, we know what's the ABCD, right? So basically we know A is going to be equal to D is going to be equal to what? 1 plus z prime y prime over 2, right? like this, how much is A? A and B, they are equal and it's going to be this much, right? Already we proved it for the medium line. But how much is the A for the, well, how much is the A for the long line? Is this much, right? So basically it should be equal to cosine hyperbolic gamma L. Right? Now, how about B? If we have a model like this, B is going to be Z prime, right? But how much is B? Here we have the B, right? ZC sine hyperbolic gamma. Right? How about C? I'm going to put it here. C is going to be, based on that, it's going to be Y prime times 1 plus Z prime Y prime over 4, which is, I have it over there, sine hyperbolic gamma over ZC. So, now I need to go calculate Z prime and Y prime based on this equation. If I calculate the Z prime, Y prime, I can put it on that model and I say, okay, this is the pi model for long transmission line, right? So let's calculate Z prime and Y prime. Z prime is clear, you know, we don't have to calculate anything. Tuesday I'll try to solve at least one problem with the transmission line, you know, to go through this kind of thing. Now, I'm not going to go through all the calculation, but Z is equal. Z prime is clear, right? Z prime is equal to ZC, what do you say, sine hyperbolic, right? Yeah, sine hyperbolic gamma. But if you do some calculation on this one, you are going to get to this. It becomes Z. This Z is the same Z for the medium line. You know what I'm saying? Times F1. Times F1. Which F1 is equal to, if you do the math, it will be sine hyperbolic gamma over gamma. See? You said the Z value, Z prime value for the long transmission line is the Z value for the medium line, the way you did for medium line, times the factor F1, which is given here. If you do the same thing, I'm not going to go through the calculation. Y prime is going to be Y times F2, and F2 is equal to tan hyperbolic of gamma L over 2 divided by gamma L over 2. So basically you can see the relation between, these are from the medium line. These are from the medium line. You said you can use the medium line, you know, values, but you have to correct them by these factors. You have to correct them by these factors. There is one good example in the book. I'll tell you which example it is. I recommend you to read this example. It's going to be example 5.2. Start there, and the next part is said, hey, first you did for the medium line, and after that you do it for the long line, and you can compare all these values, how much are these factors. I recommend you to read those examples. You know, myself, I'm going to go through another example from another day, Tuesday. But I recommend you to read 5.1, 5.2, and 5.3. It's all about this, you know, calculation on all we have here. So now, knowing z prime, y prime, we can come up with the equivalent, you know, pi model for the transmission, long transmission line. Long transmission. We have that. Any question? So you can see here mostly like a calculation, not that much of, you know, things. You know, it's mostly like calculation, you know, but you have to practice it. You have to practice it. I'm not gonna, the next part I'm gonna teach, you know, is about the lossless transmission line and power transfer and those kind of things. This part I'm not gonna give you a question to find. Just to let you know, this part I'm not gonna give you. But from here after, because the calculation become much easier, you know, I'm gonna say it's lossless. When I say lossless, the R and G, they are gone. It's gonna make the calculation much less. There's still a lot of calculation, but it's going to make the calculation much less, you know. From here, maybe you are going to have one question in the exam, you know. So this part is not going to be in the exam. Just got to practice it to learn it, you know, to know how to do this calculation. But medium voltage maybe will be in the exam. Short line maybe will be in the exam. You know, keep in mind, short, medium. This model, because there's tons of calculation, no, I'm not going to give you in the exam. But practice it. In the homework we are going to give you, definitely we are going to grade that question. Definitely we are going to grade that question. Keep in mind, you know, because this is because we are not going to have it in the exam, you know. The next part, we are going to talk about the lossless transmission line. So basically now we know the model for the full transmission line with the R and G. I'm going to go get rid of the R and G and draw this simplified model for this lossless model. Lossless transmission line. Basically, in this case, Z is a J omega L. I don't know how much I use this term. And Y is equal to, so basically this is it's going to be ohm per meter. And Y is J omega C. See, there is no R, there is no G here. For the full model, here is the R plus J omega L. And for this one, it's going to be G plus J omega C, right? And keep in mind, we defined ZC, characteristic impedance of the line. I said surge impedance, you know, in that class. Look, just correct out. We call it characteristic impedance of the line. It was, I think, Z over 1, right? Z over 1. Look at here. If it's not lossless, this is R plus J omega L, this is G plus J omega C, right? So this is a complex number. It's going to be some real value plus some imaginary value, right? But if it's a lossless, like this, yes.
Isn't Y Siemens?
Yes, it's Siemens, you're right. But in this case, there is no R and G. Look at how the ZC is going to be. So basically, ZC is going to be J omega L over J omega C. Right? J is going to cancel. It's going to be L over C. Is a real number, right? Is a real number. There is no J value. For example, it's a 5 ohm. 5 ohm, no plus J anything, right? The J part is 0. So this is the difference between the lossless transmission line and the regular transmission line, which they have a loss. The impedance characteristic is a real number. In this case, they call it surge impedance, for the system. And we'll see a little bit further down. If the load is equal to this impedance, ZC, there is a very interesting thing here. We're going to see what is going to happen. We're going to get there in a little bit, maybe in 10 minutes, something like that. But we have a lossless transmission line. RNG, they are 0. We can see the ZC, the characteristic impedance, which in this case they call it surge impedance, is just ohmic, just R value, right? That's the first thing. And let's look at the gamma. Gamma was Z1. If we replace this one, it's going to be J omega L times J omega C. So this one is going to be J omega square root of LC. Or we call it JB. So you can see gamma in this case is an imaginary number. There is no real part. Look at the previous one. We say gamma is the alpha L plus J beta L, right? Gamma L. There is no alpha. There is no alpha anymore. It's perfectly an imaginary number, right? So these are the main two things for the lossless transmission line, which is going to cut lots of calculation. And if we're going to make the calculation much less, but let's look at it a little bit more in the real way. What's the definition of this lossless line, and what's going to happen? I want to see how much power I can transfer and those kind of things. Now, before getting there, knowing these things, let's calculate the ABCD for the lossless transmission line. Basically, lossless transmission line is a special case of this, right? Is this one with the alpha L0, right? Yeah. With the alpha L0, just for the calculate. And ZC, we had some erasing. And ZC is a real number, right? It's not a complex number anymore. It's a real number. Let's calculate the ABCD for a lossless transmission line. If you do that, if you calculate the if you calculate that one, this thing is going to be equal to cosine beta x. See how much is easier than the full transmission line. It's going to be cosine beta x, and dx to be calculated. Dx is going to be J L over C sine beta x. And Cx is going to be so for a lossless transmission line, just you replace this in, I'm saying, just put the alpha L0. Just put the ZC, this value, square root L over C. If you replace those two values to the long transmission line model, you are going to get the AX, BX, and CX like. These are the ABCD for the lossless transmission line. As I said, the calculation is much less than the full transmission line. Now, if we want to find the equivalent P-pi model, again, the way we did it here and we calculate over there, right? Look at here. How much was the Z prime? Z prime was Z times F1. In this case, only there is an X, right? Because Z was the series impedance, right? Look at here. Z was this series impedance, right? So there is no R, right? So let's call it X prime. Again here, this one, there is no G. So only there is what? C prime, well, you know what we call it, you know, we call this one L prime, this one we call it C prime, you know what I'm saying? There is only C prime and L prime to calculate in this case. Now, if you do this, Z prime is going to be Jx prime. I need to calculate the x prime to see how much is the x prime. But Z prime is going to change to Jx prime, right? Because there is no R. And Y prime is going to change to J omega C prime. And it's L here, right? This is not pi model yet. So this is after here, we're going to go for pi model. So basically here, first we say when it's a lossless, right? First we say when it's a lossless, it's going to be Jx prime L. And x prime is omega, like this, omega L prime, right? L. This one is going to be J omega C prime, right? For the medium voltage line, we knew how to calculate that, right? Now we need to relate this L prime and C prime to whatever it was for the medium line. Basically the same equation, right? We need to figure out how much is this, right? And how much is this? We need to calculate F1 and F2 in this case to calculate the L prime and to calculate the C prime, right? So if you do that, I don't have it. It doesn't have it here. It doesn't have it here, but you can calculate it this way. If you do that, x prime is going to be x. That's xl. Let's call it xl. X prime is going to be xl. This is for the medium line, right? Which is the j omega L times F1. What is the F1 here? Gamma has only here j beta, right? Sine hyperbolic j beta over j beta. You can simplify this one. This one is going to be, let me write it here. I cannot remember calculus very well. It's going to be a to the j to the j beta. And there's an L. Sorry. There's an L here. Don't trust me here, you have to go check it. But what is this? This one. It's a sine, right? Sine beta. Double check it, it has been a pretty long time for me to check this one, right? So basically it's going to be sine beta over beta, right? So it's going to be XL, as I say, check this one, double check this one yourself. I'm going to leave it with you guys. XL sine beta over beta. How about the y prime? Let's call it y prime. Y prime is going to be omega CL, J, forget the J will put it later. Omega CL times what? F2. Definitely this one I'm going to leave it with you guys to calculate. I cannot remember. Then and hyperbolic of J beta over 2 over J beta over 2. This one is going to be, we can simplify, this one is going to be, definitely going to be much simpler than this one. Let me see. I'm surprised they don't have it. It looks like it's going to be this. looks like it's going to get to this one. Omega CL times tan VL over 2 divided by dl. So now you have x prime by prime for the lossless line, this one and this one. So if you want to calculate this thing, A, B, C, D, down, you can calculate it, right? So this is the model for the lossless transmission line. Now the surge impedance, we talked about it. I want to see if if I have a transmission line, it could be, what I'm putting here, it could be for single phase system, or it could be for three-phase system. I'm drawing only one phase here, right? So either it could be single phase system, doesn't matter. Transmission line doesn't have to be, it could be like a microwave systems and those kind of things, right? So it could be a single phase system, two-wire system, or it could be a three-phase system. I'm drawing the only one phase here. If the load connected here, this is a lossless, keep in mind, this is a lossless line, is ZC. I want to see what's the voltage profile of this system. I want to see what's the voltage profile of this system. I have a VS here. It's a very interesting thing here. Let's see here. VSIS, and here is a VRIR. I have a lossless transmission line. This one is connected to a load equal to the surge impedance of the line. So let's see what's going to happen. We said, if you go back to the equation, we say Vx is equal to cosine, see we calculate them here, ABCD, I know somewhere. Here, cosine beta x times VR, right? It's going to be cosine beta x times VR plus A, B, plus the next part, J, A, B, C, J over LC sine beta x times I, right? Just I wrote the voltage equation based on the ABCD I have here. This is my ABCD here, right? I said Vx, remember we said this. We said this, Vx, Ix is Ax, Bx, Cx, Dx times Vr, Ir, right? So Vx is equal to Ax times Vr plus Bx times Ir, right? This is a Vx and this is the Ax, right? And if x could be anywhere, could be here, 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 anywhere. Just I want to get to see the relation between the Vx and Vr. It's very interesting. you know. So let's simplify this one. IR, I can replace it with what? I can say IR is equal to VR over ZC, right? I can say IR is equal to VR over ZC. And what is ZC? We had somebody else. Is L over C, right? The square root of L over C. Basically, it's going to be VR over the square root of L over C, or it's going to be C over L VR, right? Now let's replace IR over there. Let's replace IR over there. So Vx is going to be cosine beta x times VR plus J L over C times sine beta x times IR, I'm going to replace it here, C over L VR. L over C times C over L is going to be what? 1, right? So basically this one is going to be Vx is going to be cosine beta x VR plus J sine beta x VR, right? So let's factor in VR is going to be cosine beta x plus J sine beta x. Or is equal to what? VR e to the power of J beta x, right? Or let's do this one. I like the angle with it. Beta x, right? What does it say that? I calculated Vx is equal to VR with the angle of beta x. Does it say that magnitude of Vx is equal to magnitude of the other side, which is a VR, right? So basically this one is telling me, this last equation is telling me so that here, this last equation, I write it again here. Vx is equal to VR with the angle of beta x. So, right? Angle is there. There are some angles. It's going to be different. What does it mean that? Let me plot that. Let me plot that. I'm going to plot this. This is the x-axis, and this is the Vx. What does it say? Right? From 0 to how much? To L, right? You think this is interesting? The voltage is flat, no drop. See, that's a kind of characteristic of this impedance. If you have this kind of impedance at the low, the voltage profile would be flat. But if it was a lossless line, not lossless, it was a regular line, what's going to happen? What's going to happen? Vs is going to go like this, right? It's going to drop, right? If it at the beginning, it's going to go this way. There are two cases. Because this is the end, right? And this is the beginning, right? So basically, it's going to go like this, right? Vs is more than V, and there are two cases: leading power factor and lagging power factor. This is for the lagging power factor, right? It's going to be like this. If it's a leading power factor, it's going to be what? Under, right? So is going to go down. Leading and lagging. Right? Remember the one I draw for the short line? Vs was smaller than the VR, right? For leading half angle. They call this one SIL. SIL. Surge impedance load. Your load is equal to surge impedance. So if the load is equal to surge impedance, the voltage profile, and it is lossless line. It's a lossless line. The voltage profile is perfectly flat. But even if it is not lossless, right? Now we got a feeling about it. If the load is equal to the surge impedance, not surge, characteristic impedance, it's going to become kind of flat. Not exactly flat, but it's going to be very, very close to flat, right? So this is the main characteristic of the surge impedance. If the line is lossless and the load is equal to the surge impedance, the voltage profile from the beginning and to the end is going to be flat. So what time is it? So we have a little bit more to go. There are two more topics I want to talk about it, and we are done. You know. Let me make sure the scale here. I went from 0 to 12, maybe this one went from 10 to 0. Oh, so your book, just keep in mind, if you check your book, here is the x equal to L, you go the other way. You know what I'm saying? If you put the L first here, and you see it, if you read the notes on the things, you see it's opposite of what I'm putting here, because they put the L here and 0 here. So this will be going to be opposite. You know, just to, if you see this one doesn't match that one, is because of this. Because I put 0 first and L and then what they have in the book is other way. We're not going to get to the power flow calculation, unfortunately, in the chapter 6. We cannot get to that chapter 6. But here, just I'm going to talk a little bit of concept of power flow. You know, how the power flows between two bus bars. You know, for example, from the receiving end to the sending end to the receiving end. You know, just I'm going to calculate the active and reactive power for those kind of things. I'll do it first for the short line because that's very easy. Let's do that one first. And after that, we'll come back here, we do it for the lossless line. I don't know what to call it, you know. We call it a steady state stability limit. A steady state stability limit. So let's go to the short line first. Let's go to the short line. Because it's easier to start with that. And I call this one R and this one S, right? And I have a VS here, and I have an IS here, and I have a VR here. I'm going to put it this way. VR, I'm going to keep it as a reference. It's going to be VR with an angle of 0, right? And this one is the IR. and this one is going to be Vs, and it's going to have some angle. We call it Vs with delta. I give it a name delta. I'm going to use this one later for synchronous generator. The same thing I'm going to use it for synchronous generator now. Tuesday, maybe. Tuesday, and the next Tuesday we are going to talk about the per unit system. Just I'll talk a little bit about how to model the generator, very, very short. Because that one is a very, very extensive, chapter. Just very, very simple. I'm going to talk about that. And after that, we know how to model the transformer, we know how to model the transmission line, and we know how to model the generator and the load. We're going to get to the per unit system. That's very important thing, but very simple. And we're going to have one question on that one in the final exam. So this thing, I want to come up with a power flow. So I have to think about it. If I'm going to show it here, I have a one bus bar here, right? This one is connected through a transmission line here. Usually here, there is a generator. And usually here, there is a load. Right? Could be other way. Just I put it this way, Now, I want to come up with a PQ here. P plus JQ. I want to calculate this. Okay, let's just start to calculate the P plus JQ here. Which is the S, right? We said S is equal to, I treat it like a single phase system, but later on if it's a three phase, we times it by 3, right? This is one phase. I'm doing this for one phase. If later on it's three phase, we just times it by 3, okay? So S to the VI, or either it could be VSIS conjugate. Let's see which side you want to calculate. Now this is important. I'm going to calculate on the generator side, on the source side, right? So let's call it SS. There is the SS, it's coming from here, right? There is the SR here also, right? We can calculate those, Let's calculate SS. So it's going to be VSIS conjugate, right? How much is the VS? VS with delta, right? Fine. Let me calculate the IS here. How much is the IS? You tell me. VS with delta minus VR with 0 over R plus JX. Or R plus JX, I'm going to call it Z with delta, theta, with theta. I'm going to call it Z with theta, okay? So, this one is going to be Vs over Z with delta minus theta, right? Minus VR over Z minus theta, right? That's the IS. Is it correct? Let's plug it into that equation up there. So it's going to be times, if I conjugate this one, the only thing is going to be, this one is going to be negative, and this one is going to be negative, right? So it's going to be Vs over Z with a theta minus delta minus VR over Z with theta, right? Let's time down. Let's time down into this. It's going to be Vs squared over Z with the angle of how much? Correct? Correct or not? Because it's a delta plus theta minus delta, right? Delta plus this, right? So minus Vs VR over Z, right? With the angle of how much? Theta plus theta. Correct? Theta plus theta. Now, let's see how much is R the P and Q. how much is the P? How much is the P? It's going to be real part of this, right? And how much is Q? The imaginary part, right? This is a general equation. I calculated for the short transmission line, right? Let's do a little bit of approximation here, because usually R is much smaller than X. Let's say R is much smaller than X. Basically, Z is equal to JX, right? If Z is equal to JX, how much is the theta? How much is the theta? Basically, here these are the magnitude of Z, you know, because already I put the angle, right? Already I put the angle, right? So basically, this one is set, and how much is the theta? 10. Let's replace them here. Let's replace them here to what we are going to see. P is going to be something cosine 90, right? Cosine 90 is how much? So this can proceed, right? Minus VSVR over X cosine 90 plus delta, right? How much is the cosine 90 plus delta? Minus sine delta, right? Minus sine minus positive, right? So basically it becomes VS VR over X sine delta. Let's calculate PS. I mean, these are this side. I'm calculating it here. Right? I'm calculating in this side. How much this is concerned. How about QS? So let's put it here. It's going to be, this one is the 1. So it's going to be VS squared over X minus VS VR over X. That one is sine 90 plus delta is going to be cosine delta, right? Which I can factor in Vs over X. So it's going to be Vs minus Vr cosine delta. Right? The equation are simple now. Basically, when I assume R is 0, I'm assuming this line is a lossless, right? Like basically, first of all, I say, hey, forget Y, right? And after that, I say, hey, let's assume R is 0. This is like a lossless system, right? But let's plot this one. Let's plot this one. And let's assume Vs and Vr, they are constant. Let's say Vs and Vr, they are constant. Let's plot this one. Very important characteristic of the generators or the sending gen. What does it say here? It says, hey, maximum I can give you this much, right? If you put a load, let's say this number is 100 kilowatt. If you put 150 kilowatt here, what's going to happen? What's going to happen? This is a very interesting topic, you know. Remember, I have been in San Diego 5 years almost. I think it wasn't the first year I was here, like 4.5 years ago. We had a blackout here. Remember? Can you remember that? What happened? You know, I mean, like 6 hours, 10 hours, everywhere was kind of shut down.
Yeah.
This delta has a lot of meaning, physical meaning. This is not just a math calculation here. As I said, here is what is a generator. Later on, if those when they take the course in the M121, we will explain. This is a synchronous generator. There are two fields. One is a stator, one is a rotor. There are basically two magnets. They are rotating together, and you can see as soon as you put two magnets next to each other, they're going to generate force, right? Or they're going to generate, if they start to move, they're going to generate voltage or current, right? This delta is the angle, real angle, between the magnetic force of the rotor stator and the magnetic force of the rotor. So, when these two, they can generate the maximum force or the maximum energy when they're 90 degrees, right? So, if you put 100, we said, hey, here is 100 kilowatts, right? The maximum they can provide is 100 kilowatts. So, if somebody has 150 kilowatts, say, let's say, originally it was like 30 kilowatts, right? I don't know, 30 kilowatts is going to be, for example, 20 degrees. This is delta, right? We have a load and the system is working, everybody is happy, delta is 20 degrees, right? Now you suddenly put a big load here, right? 150 kilowatts. More than the capacity of the generator, right? What is going to happen? Let's say first, the limit is 100 kilowatts, we had a 20 kilowatt, now we change it to 80 kilowatt. What is going to happen? These guys, they are going to start to open this angle, right? To generate more power. So basically this delta was here, now we have a load change, it's going to go, I don't know, for example, 85 degrees, right? We need to calculate how much is that, it's very simple. Now somebody puts more load. What's going to happen? This poor guy said, hey, I have to open up this one more and more and more, right? But after 90 degrees, I'm not doing anything, right? After 90 degrees, it is getting worse and worse. What is going to happen? This delta is going to go like this. And as soon as you pass 90, not 90 exactly 90, a little bit more than 90, and you cannot provide the load, you are done. Your system is going to get unsynchronous. The generator is going to speed up, speed up, speed up, speed up, or it's going to slow down, slow down, slow down. So the relays in the system, as soon as the generator speed, past some limits, you know what I'm saying? They're going to shut down the generator. So what is going to happen? Just I'm going to tell you what happened, 5 years ago. An engineer had a mistake and shut down one of these generators by mistake. It's a power plant. This generator is a power plant. Now, hey, we have a lot of load. You took one source out. What's going to happen? The rest of the generator they started struggling. Hey, let's open this angle, open this angle. First one goes over 90, boom, that one is out. The next one out. The next one out. This is like a chain reaction. Suddenly all of them are gone. You know what I'm saying? And you get black. This is one mistake. They call it dispatching. Power dispatching is a very important part of the power system analysis. If you go to the SPGA and those kind of things, the load management. You have to know how much load you have, and you make sure you are somewhere here. You know what I'm saying? If the load comes in, you have still some space to go. You know what I'm saying? You have still some reserve to cover it, right? If you design it for here, what's going to happen? Boom. As soon as you have a little bit more load, boom, you're unstable. Usually for power plant, for the generator, this delta is less than 30 degrees. This delta is less than 30 degrees. Another thing we talked about is leading lagging power factor. These are not just math. There are lots of physical meaning behind this. Think about these wind generators. They are again synchronous machine. They are going to go sit on top of a tower, right? What's important over there when you are going to put the generator up there? What? That's one way. But another thing, you want as small as possible generator, right? You're going to go put it like 30 meters up there, right? So if it's a heavy generator, the tower has to be very powerful. It still is powerful, but compared, you have a generator that is half the weight of what it is, the other one is, right? It's going to help you a lot with the structure. For the wind generators, those wind towers, they design them with a leading power factor. Because leading power factor is going to cause to reduce the size of generator. Generator is much smaller. So if you look at if you see somewhere, all those ones, they are in the power plants, they are lagging. They work with the lagging power factor. But those ones, they are on the wind towers, they are leading power. They work with the leading power factor because it's going to help them to reduce the size of generator, make it much smaller. The smaller is going to be much easier to install it up there in the top. So they call this one limit. Limit of this power generation. We never ever go close to that. We are not that dumb to design the system to cover just this much. You know, half of this, that's enough. There is a chapter in this book, or every hard analysis book, it's called stability analysis. Usually it's toward the end, you know, it's a pretty advanced topic. If you want to look at what I said here, just look at that chapter. Explain it very well what's going to happen, how the system can get, you know, stable or not. But let's look at here. Let's say the load is here. This is the load. We are here. We are working here, right? We are here. Let's say we have a load change. The new load is here, right? The new load is going to be here. But this one is not going to go exactly from here to here. What is going to happen? This delta is going to go up, come back, go up, come back, go up, come back, go up. Basically, if you look at the delta, it's going to be like this. Something like that. If you can calculate exactly. If the load is very big, even you put it here, still you are not going to limit it. If you pass somewhere here, you are not going to come back again. There's a limit. If you are interested, go read the book. Usually it's chapter 12, 11, very toward the very end. It does calculate all these kind of things, you know. Yep.
So then how did it fix the blackout error? You say you can't.
Oh, to fix the problem. It's very difficult. Let me tell you this, you know. Somebody is coming with something to hit you, you know, and you have 1 second to react. Maybe you cannot do it, boom, he hits you, you know what I'm saying? That's what's going to happen. Because sometimes we do something, even we make it worse, you know what I'm saying? But if you are fast, you should shut down some areas very quick to reduce the load. You know what I'm saying? For example, you shut down San Diego, you should not shut down Orange County, because the power was coming from Arizona, you know what I'm saying? You have to start to shut down the load. If you are fast, so some areas they're going to lose the power, but still some areas they're going to stay on power. But maybe you shut down too much, again you're going to fall from the other edge, you know what I'm saying? That's something you have to be careful, you know, it's both edge, you know what I'm saying? You have over generation or you don't have enough generation, you know what I'm saying? Either way it's going to cause you a problem. Yeah.
I was going to say, is that similar to how like the NEMA motor curves work when you're like the torque?
Yeah.
Okay.
We will talk about this in the next class, and next quarter is about the synchronous machine and the torque curve and those kind of things. We'll go to the detail of those kind of things. They're pretty, you know, synchronous machine. There are three types of machines: DC machine, induction machines, and synchronous machine. Synchronous machine, they have different kinds. They have a reluctance machine. They have a permanent magnet machine. All these electric cars, you see, Toyota, Nissan, GM, all those guys, not Tesla. They have all permanent magnet synchronous motor. So they are very high torque. They are very good for they are very small. Think about it. This is an electric car, right? It has to move around. It has to carry out that weight. You don't want to put a big bulky motor over there because it's gonna dissipate lots of the energy of the batteries, right? They use the permanent magnet machine. We're not going to discuss that one in the next class, but that's another type of synchronous machine.
What if you have just a little bit more power being like a little bit more load than you're providing, or a little bit less load than is being provided? That would cause the frequency shift?
No, that one is different. That one, they call it group control. That one they call it group control. And I don't want to talk about it here. But as soon as you have more load, the frequency in the power plant is going to drop. But what is important, that's at the load. You know, how much is the load? We want to keep it 60 hertz plus minus maybe 0.01 or 0.02, you know what I'm saying? But in the power plant, it's going to change more. We are not worried about that, you know. Maybe change like 0.2 hertz, something like that. But they call that, they call it group control. That's very funny. You know, let me tell you, this group control, all these things I talked about, this is about the synchronous generators. But nowadays, they are trying to implement this in power electronics. Power electronics, you could have an inverter. Inverter is a DC to AC converter. So basically, convert the DC power to the AC power. Now, they're trying to model this power electronics box like a generator, like what we have here. The advantage of doing it this way, see, there are two modes of operation for every inverter. The one they are used for utility, I'm saying, not the one is used for motor control and those kind of things. Either your inverter is connected to the grid, like all this solar they install it at home. They are connected to the grid, right? You are connected to the grid, and you are having a small source here. You see, if you look at it, this is you at home. You have a small generator, and this is the grid, right? And your load is here. You are here. And here you are connected to the rest of the grid, right? So you have a generator at home, which is the solar and the inverter. It's not conventional generators, right? Still there is an impedance here. Those when they have power electronics units, it's the output filter we have. So you consume power here. So there are two modes. Either you connect it to the grid, which is very good. You are connected to a stick place, right? So this guy can generate as much as you want. If you are using less than here, if the usage here is less than the generation, you are going to put it to the grid, right? The surplus is going to go to the grid. If here you are not generating enough, it's night time, right? You don't have any generation, you get it from the grid, right? So they call it grid type operation. But think about it. Somehow the grid is gone. It's just you, UPS mode, right? Lot of you are familiar with UPS. They call it a standalone operation. A stand. Nobody is there. A standalone operation. These are two different modes, you know. These are very deep power electronics, you know, control concept. To switch this mode, you know, you are grid type, you are off grid. There are lots of transitions going on. Nowadays, they are trying to use this concept of, they call it group control. If you are interested, just type it in Google, you know, it'll bring it for you. Group control, they are saying this is a new mode for in this inverter to control it. They're going to say, hey, I'm going to be like a generator. I don't care if it's grid there or not. If grid is there, I'll go follow this equation. If it's grid is not there, I'm going to support my load. You know what I'm saying? There is no transition. Grid off, grid on, grid off, grid on. It's a big transition for inverters, you know. Now they call it seamless. They call it seamless transition. Load, this is very important. Load doesn't see any flicker, anything. Grid is gone. But load doesn't sense that. See how good it is. Think about it, you know. This is very important, you know, for sensitive load, you know. The grid is gone. We had a source here, but we didn't feel it. They call it seamless transition, you know. They use a group control to model this, you know, power converters, this kind of thing, to control the system. This is a very, very advanced topic in the power electronics and control.
I don't have solar personally, but if you had solar in your house and you were using an older inverter and made that switch to the grid, do the lights in the house flicker?
No, let me tell you, nowadays, I can tell you, maybe, because I'm working for a project, it's for Outback Power, they are based in Seattle, part of Alpha Technology. We are working, I think we are going to be not we, basically them, because we are not going to see any name of us, because we develop everything, but it's going to be under their name. They are going to be one of the very, very first ones. They have these things. It could be on-grid, off-grid. But right now, all the solar that are installed, I shouldn't say all, maybe more than 90%, they are only grid type. As soon as the grid is gone, you cannot generate any more power. They force you to shut down. Think about how bad it is. You know, I have all this power here, I cannot generate anymore. You know what I'm saying? Right now, the rule is as soon as the grid is gone, you have to shut down. You are not allowed to generate any power. But they are changing the rules, you know, and they are coming with a smarter system, you know. So even the grid is gone, you should be disconnected, right, from the grid. You should make sure you are disconnected. What's the problem if you are not disconnected?
No power.
So for example, a CGA guy, I'm coming to say there was something here. I'm coming to fix the line here, and I still am connected here. And here, I'm thinking, hey, the grid is gone, right? It should be a whole system, right? But somebody here is generating power. You know, that's the thing, you know. You should, they said, if you are in the islanding mode, they call it islanding mode, you should make sure, within a very, very short time, if you are going to stay hot, you are going to continue to generate power, you should disconnect. These are very, very advanced topics in the IEEE, you know, communities. They are talking about this thing because there are lots of stability, lots of things going on, you know, to come up with the new rules. Okay, how should we write the rules? You know, everybody follow that to not cause problems. First of all, they can operate and will not cause problems for the rest of system. Those kind of things.
So is group control like an inverter that's the smarter?
Group control is a concept for generator, synchronous generator, all systems. But the power electronics side, we are trying to employ that concept to run the inverter like a generator. So the best advantage of that one is it doesn't carry the connectivity is really good.
So you can be off grid and never.
Exactly. So this one was for the short transmission line. This one was for short transmission line. Basically lossless transmission line. And we can see the limit is this much. Look at the Q here. How much is the PR? Can somebody see? I calculated SS, right? I could have calculated. You do this one yourself. SR is going to be VR. IR constant. I'm not going to calculate the rest. No, I'm going to leave it with you. But can you tell me how much is going to be PR? PR. It's very simple. Very, very simple. Very, very simple. And this one is 1. Last one. No. PR is both PS, right? So you send the active power here, right? If this one is 0, right? If this one is 0, there is nobody to here to dissipate active power, right? This one only can dissipate reactive power, right? Right? So basically PR and PS they are the same. If you do all the calculation, PR is going to be the same thing. VS, VR, or X sine delta. But Q is going to be different because there is some dissipation. That's it. There is a little bit more equation. You can read those ones, but basically very, very similar to what I said here. You know, is on 286. You can see at the end they get to the same equation. Very similar to this one, but basically they put shunt here and shunt here. More losses. Look at the page 268 yourself. You know. So I'll send you the second homework 5, not tonight because tonight I think I'll be busy on this very, very late. But tomorrow we'll give you the homework number 5. And homework number 6 is going to be 2 or 3 questions. No, not more. And we'll either I send that one also tomorrow if you guys will have all of them, or maybe a little bit later. But homework 6 is going to be one question in the final exam. You'll work on that. We'll go over one example on this one Tuesday, and on the payment system, I'm going to go over one example for the next Tuesday. And you know, it's too early to say, but have a happy time.
Like 12.